Hello students, it's Instructor Howard again, and we're going to work through what I think is probably the most difficult lecture that we have this term, and that is on the idea of a spatial reference. So we're going to take it pretty slow. When you're studying this material, you should be able to draw out this type of outline and understand what each part of the outline means. So here we go. So essentially, a spatial reference is simply how we get our geospatial data to know where it is on the surface of the Earth. Okay, and more precisely, how do we get a three-dimensional surface for the Earth down to 2 dimensions? Okay, and so that's called the data's spatial reference, is the process that it underwent to get to 2 dimensions and the process it underwent to tell it where it is on the surface of the Earth. And so having different spatial references can affect how your data displays in your map and how different data types or data sets will actually interact with one another. Okay? And so that's the larger concept, is this concept of a spatial reference. The aspect of the spatial reference we're going to focus on in this class is called the datum. Okay? And so this is one aspect of a data set spatial reference, is what datum is it using? And there are 2 components to a datum. The first is the datum's ellipsoid, and the second is the datum's coordinate system, or you could also say its point of origin. Okay, either one of those is correct. So the ellipsoid, this concept here of an ellipsoid, this means essentially the surface of the Earth is irregular. Okay, it's got mountains, it's got oceanic trenches, and not only that, but because it's rotating, that causes its liquid interior to bulge at the equator because of the centripetal motion. And so that makes it a spheroid instead of a perfect sphere. Okay, so a spheroid just means something that is an irregular sphere or like a sphere. And so what we have to do is, because we cannot mathematically represent a sphere, a spheroid, what we do is we take an ellipse and we spin it around its y-axis, and that creates what's called an ellipsoid. So it's a 3-dimensional ellipse feature, and we can mathematically represent an ellipse. And so that ellipse will pass through certain parts of the Earth more accurately than others, and so the purpose of our map determines which of the ellipses we're going to use. And so if we change ellipses, we change datums, and so therefore 2 data sets are using different ellipses are actually using different datums, and they have different spatial references that way. And so there's courses you'll take that explains how the math behind the ellipses work and everything, but just remember that if you switch the ellipse that you're using for your data set, you've switched the datum, and they therefore have different spatial references. We're going to focus a bit more on the second component of a datum. So remember, a datum has 2 components, an ellipsoid and a coordinate system. And so we're going to look a little bit more at the coordinate systems. There are 2 types of coordinate systems. There's what's called a geographic coordinate system and a projected coordinate system. So these are kind of 2 large groups here. There's many different coordinate systems within each, but they will fall in as either geographic or projected. And so we're going to first focus more on the projected ones, and then we'll go back and grab the geographic ones to finish. Okay, so within the projected coordinate system group, there are 3 families. Okay, that's why you have to learn this kind of as an outline. So these 3 families here are all projected coordinate systems. And so if you gave me a projected coordinate system, I would know that it would be within one of these 3 families here. And so we have what's called conical, cylindrical, and my personal favorite, because it's fun to say, azimuthal. Or if you're not quite as on the fun side, you could say planar if you wanted to. So we'll look at each one of these, okay? And this is essentially how we, with the projected coordinate systems, what they've done is they've taken a 3-dimensional system, or a surface, and they, in theory, this is theoretically how it works. It's like taking a piece of paper and wrapping it around the surface of the Earth, and then projecting the Earth onto that piece of paper and then unwrapping it and getting a map. Okay, so that's not how it works mathematically, but that is theoretically what's going on, or in principle what's going on. So we'll look at the three families here. We'll begin talking a little bit about what some of the ideas behind these, because you'll see here, so when you were in grade school, they probably had a map on the wall, and it probably looked something like this. This is called a Mercator map, and what you've probably noticed, hopefully, is that in this type of map, Greenland up here looks absolutely huge. It looks the same size as South America does, and almost the same size as Africa. It's not. Okay, so what's happening here is because we've gone from 3 dimensions to 2 dimensions, that introduces distortion. Okay, and so these Mercator projections, they are a projected coordinate system. They're in that family or that group, and what happens is we just always have some form of distortion when we go from 3 dimensions to 2. There's no perfect way to do it, and so I'll tell you which family this is in a second, but that just gives you an idea of how distortion does occur when you go from three-dimensional surfaces to 2 dimensions. And so we're going to first look at the conical family. And so what happens with the conical family is they take the three-dimensional surface and they kind of give it a birthday hat. Okay, so they'll take the piece of paper and they'll wrap it around like a birthday hat and then project onto it and then unfold it, and then it looks like this right here. So now we have a 2-dimensional map. Okay, and now this blue line right here is really important. This blue line, which is where the projection actually touches the surface, is called the line of tangency. Okay, line of tangency. And that's important because that's where the least amount of distortion takes place. So if we go back and we look at this Mercator map, the line of tangency would have been at the equator, okay, which is right about here. And so everything at the equator is most accurate. This is where the least amount of distortion is occurring. And then as we move away from the equator, the distortion increases. That's why Greenland's so distorted in this map. And that's why Antarctica looks way bigger than it actually is in this map as well. This is not a conical one. I'll explain that this is a cylindrical one, but the same principle is taking place. So you'll see that the conical one has a line of tangency that runs this way, runs east and west, and it is one of the lines of the parallel lines called lines of latitude. Okay, and so that's important to know, is that with a conical projection, your line of tangency is going to run east and west. Okay, so let's look at another type. This is the cylindrical family, and what they did here is they took a cylinder and they wrapped it around the earth and projected onto it and then unfolded it. And that is what this Mercator map I keep going back to. It's a cylindrical one. You'll see this map here looks exactly the same. And again, Greenland looks absolutely huge in this map because of the distortion towards the poles. Same thing with Antarctica. Look how big that looks. It is not that big. And so the line of tangency in a cylindrical one going this way is running along the equator around this way. So they're really nice for a world map, as long as you know that the size of the objects have been distorted towards the poles. The next one is the azimuthal one. And so with the azimuthal maps, what they've done is they take a disc or a sheet of paper even, and they just touch it to the surface at one point and project onto it like this. And what that does is that creates a point of tangency. So they have one point where it's most accurate, and then as you move out from that, your level of distortion increases. And so those aren't quite as common. They're pretty common for polar maps like this. You know, if you want a map of where Santa lives, or for things like Alaska or Hawaii, where you have a kind of irregular shaped object or islands that you can make just a single map of, where you can have that point of tangency. Okay, so those are the three families there: conical, cylindrical, and azimuthal. Conical and cylindrical are more common, but you possibly could see some azimuthal stuff in other classes. Okay, so now we're going to move on to another concept here. And that is what is known as universal. Let's make sure I get my spelling right here. Universal transverse Mercator. Okay, also known as UTM. And what this is this is part of the cylindrical family. Okay, it's part of the cylindrical family, but they've been kind of tricky about this. So what they said, I'm sure this is exactly what they said. They said, you know, why don't we just flip it on its side? So you'll see here with the cylindrical family, the line of tangency runs this way. But what if we flipped the cylinder on its side and ran it this way? Okay, east and west. Then our line of tangency would be a meridian or a line of longitude. And if our line of tangency is a line of longitude, we can then turn the Earth and run that line of tangency through any section we want. And so they did that. And what they did is this. So they turned the Earth 60 times, and they created 60 zones of what's called universal transverse Mercator. And we are in zone 10. So this is interesting because you now have a line of tangency that runs through your zone, and so it's really good for like county data or something that's a bit more zoomed in, but you can then just turn that zone and run it through anywhere you want. So if we wanted a map of Florida, this would be a good one because you see Florida's in one of the zones. Oregon's actually split by 2 zones, so Klamath Falls is in zone 10, but like Lakeview's in zone 11. So like I said, if you're zoomed in more, this is an excellent way to project your data. It's important to realize though that because there's 360 degrees and there's 60 zones, each zone is 6 degrees wide, which means that it has 3 degrees on each side of the central meridian of the zone. It's also important to realize that the UTM, so Universal Transverse Mercator projections, they use, like I said, there's 60 zones. Each zone is 6 degrees wide, and then it's in meters. Okay, and so that's actually pretty cool because if you're using a GPS unit and you can see the coordinates on the unit and it's in UTM, it's going to show it to you in meters. And so you'll actually be able to figure out exactly how far away from something you are, whereas if it's showing it to you in latitude and longitude, it's very difficult to know how far a degree is or a 60th of a degree or something like that. So the meters part can be fairly handy with that. And so that's what when we use the term UTM, that's what we're referring to as Universal Transverse Mercator. And so we have one last concept here that's important is 2 concepts actually. The projection that you're going to use is determined by the orientation of your features that you're mapping. So what do I mean by that? Well, if you're mapping something like Tennessee, the state of Tennessee is very oriented east and west, right? It runs east and west. And so I'm going to choose a projection where the line of tangency runs east and west through that state. I wouldn't want one that went north and south. But if I'm having a feature that is running north and south, such as Idaho or Vermont or New Hampshire, then it would be very nice to have a projection that runs its line of tangency, such as UTM, where it runs north and south, and will then run through more of the feature than if it ran east and west. And then the other thing we have to remember is, if we want to know what are the 4 elements that can be distorted by spatial references or projections, we just have to remember that spatial distortion makes us sad. Okay, this is just kind of a fun way to remember this, is spatial distortions make us sad. And so what that means is that the 4 spatial elements that can be distorted are shape, area, distance, and direction. Okay, shape, area, distance, and direction. And so what this means is that particular projection families will often preserve one of these really well. One of them will be preserved acceptably, and the other two will be really bad. Okay, so for example, the one that we've been using in the class is 1983 North American Datum 1983 Albers, and that's an equal area projection, and so it preserves the area of the features really well. And that makes a lot of sense because at the Forest Service we want to know a lot of things like how many acres have been burned or how many acres of owl habitat will be affected. And so we're more concerned with the area than we are so much the distance or the direction. But if you were using a map to navigate with, you would want to preserve distance and direction more so than shape and area. And so we don't, there's no perfect way to do this. You cannot preserve all four. So again, the orientation of the features you're mapping and the type of features that you're mapping will determine which of these you want to preserve. And so therefore, which of the projection families you want to use. And we're going to close up real quickly with the last type. So those are all projected coordinate systems. We're going to close up here with the geographic coordinate systems. And what you have to know about those, so geographic coordinate systems, let me just type here. So we have geographic coordinate systems. And what's important to remember with those is that they use latitude and longitude. So if you're looking at your map and it's giving you map units in latitude and longitude, that's a good hint that your spatial reference for that map is in a geographic coordinate system rather than a projected coordinate system. And so we're going to talk about latitude and longitude in the next lecture, which will be a shorter lecture. But I just want to tell you that if we're talking about latitude and longitude, we're talking about geographic coordinate systems. Okay, so I hope that makes some sense. It's not an easy concept, but if you just learn kind of the outline that you have spatial references, you have each spatial reference will have a datum. Datums have two components, which are its ellipsoid and its coordinate system. There are two different groups of coordinate systems, geographic and projected. Within the projected coordinate systems, there are three families: conical, cylindrical, azimuthal. And then with geographic coordinate systems, they use latitude and longitude. If you can just learn it that way and you can explain it to somebody else that way, you'll be all right. And then just also study up on what UTM means, Universal Transverse Mercator. And that's just a cylindrical projection that's been turned on its side, and it has 60 zones. So they can run that line of tangency through each of those zones. Each zone is 6 degrees wide, and that the UTM uses meters as its units. So just kind of those types of things, if you learn those, you'll be fine. And so if you have any questions, you guys can always shoot me an email or message me and I'll get back to you. And thank you so much, and I'll see you next time.